we're up to episode 14 of our retro core dev. This time we're looking at the bullet rendering circuit in the Tank Battalion game. I'll be looking at how it works, and then we'll implement it in Verilog. Alright, well this episode we're getting into the circuit that renders the bullets on the screen in the Tank Battalion game. Now, up till now we've looked at the tile map circuit, and now this is going to be the bullet circuit. So the bullets we're talking about in the Tank Battalion game are what we're seeing here on the screen. Bullets are fired by the enemy tanks and also the main player in the game. And they fire, and when they hit, obviously it explodes the tank. Main thing to notice here is that the color of the bullets are blue in MAME, and as we'll see, that's actually impossible in the hardware. They have to be white. So one thing we've scored already over the FPGA version of this game is that it's better than MAME, because it's closer to the original hardware. So on the screen here we've got the chips that make up the bullet circuit. We've got our familiar latch here that takes in the data, and then so this data gets latched. It works its way two ways. This item here is the vertical counter or delay circuit, and this is the horizontal delay circuit, and I'll explain how all that works coming up. And this bit here is just our PROM, our color PROM, with our RGB outputs, and you'll remember that previously we were using A7 down to A2 for the tile map, and then when we had a pixel to be rendered we were using that A0. Now here we're using that A1. That's now the input to our bullet. Now just a quick explanation about how this works. We've got the PROM chip, the 3L PROM chip, and as we said, the A1 is the input from the bullet renderer. So it has been 0 up till now. We've just set that to 0, but now we're going to have an input based upon whether there's a bullet there or not coming out of the render circuit. So I've just put together two examples for the data shown below is the table for the actual color PROM, and we had the address here 0 to FF in terms of the inputs, and then we get an output nibble which is going to tell us what color that we have, and I've color coded these here. So 2 is red, green is 5, yellow is 7, cyan is C, and then everything shown as E is white, and so is F. So with an example here, I just typed in hex value of 81, which is binary 10000001. So effectively the input 7 down to 2 would be that there, 1 with a bunch of zeros, and then if we have the pixel on, that would be 1, so that's 81 hex. So if we look at for 81 hex here, we've got 8081, so that would be it would be a yellow pixel on the screen. Now if we add that A1 equals 1, it becomes 82 or 82 hex, and you can see that flips over to here, and that is E. So we've got our bullet on the screen, which is our bullets are all white. So you can see anything with this 2 is going to be white, same with the 6, A, and the E is always going to be white. So our bullets are always going to be white. Now interestingly, something to mention is if we've got both a pixel from the tile and we've got a bullet, that's going to equal 3. So you now have 1 plus 2, because A1 is a 2, so 1 plus 2 equals 3. The priority is the tile. So basically the tile would go over the top, the yellow pixel would go over the top of the white bullet. And we'll see that when we fire up the test screen later, that the tile map does actually go over the top of the bullets. Just another example here, if we put in FD hex, which is 11111101, so again that's the tile identifier, if you will, that's the pixel for the tile, and then that would be the bullet pixel. First it's 0, so FD, go down to here, FD, so that's going to be a cyan pixel, let's say for one of the tanks, and then when we make the bullet, it's going to be A2 is going to go 1, so then that goes to here and it becomes E again. So again we see all of these bullets are always going to be white. So hopefully that's clear how that's demonstrating the bullets showing on the screen through the RGB. So for our bullet renderer, the screen is completely separate to the tile map renderer. So it's got a different coordinate system. It basically lays on top, very similar to how like a Commodore 64 sprite system might work. It's not related to the background tile map at all. So the screen coordinates are not 8x8 squares in this case, they're just 0 to FF, both vertically and horizontally. And the 00 is from the bottom left, but don't forget that this screen would be rotated for the actual game. So the left hand part of the screen would be the top of the screen. But in terms of understanding this bullet rendering, it's definitely important to have it set up like this, because this is how the raster works, obviously. Now not all extremes of this are shown on the screen. So 00, if you put a bullet at 00, you wouldn't see it. So some of the extremes of this grid here are cut off. So what happens is the memory up here is the 0 page memory. So our workram 0, if you remember from previous episodes, 0000 all the way up to F, is going to accept 2 entries for a bullet. So there are 8 bullets, and each entry would be 1 bullet, as you can see here. So 0 and 01 is an X and a Y. And what I've done is I've put together a little example of putting a bullet at 4882. So 48 is the displacement vertically, and then 82 is the displacement horizontally. And what I've done is I've set each bullet to be the same. And the reason for doing that is if we do that, they all look the same when we go through it, and we won't see multiple bullets. It will be much easier for us to understand what's going on just by seeing 1 bullet in the simulation. So what I've done is I've preloaded with a data file the workram 0, and I've just put the 4882 in these first locations 0 to F. And then what that does is it just forces the hardware to show the bullets at 4882. I'm going to break down the bullet render circuit into 3 important blocks. 1 block is for the vertical delay circuit, and 2 are for the horizontal delay circuit. As you can see here, I've pulled up the circuitry that's responsible for ensuring that the bullet is shown at the right vertical position on the screen. It's made up of the input latch 2L, 2 LS283 adder chips, an 8 input NAND, and a D flip-flop, and a couple of extra NAND gates. If we have a look at this diagram, we can see what the vertical delay circuit is doing. We have the coordinate reference in the bottom left as 0, 0, but the actual screen plots from the top left due to its raster display pattern. So in order to block the vertical position correctly, we need to invert the bullet vertical offset position by adding the required delay. This is done for checking when the required delay plus the position offset is equal to close to FF, as we'll see. In fact, the designers of the circuit made the check FC, FD and FE to allow the bullet to be 3 lines wide in the vertical direction. So here you can see our 283 is a 4-bit binary adder with fast carry. And what that all means is we've got an A input and a B input, and then we've got a sigma output, and we've got a carry. So it effectively will take in your value for A, add it to a value to B, and then it will have a sigma value for that one. In this diagram here, I have done a simulation, and I've pulled in certain wires that we can look at because it's quite difficult to get our head around how this is working. You're going to need to look at it a fair bit. I'm going to try and explain it as best I can, but it might need some looking at. So effectively, as I said before, we've got our most significant byte, not bit, and least significant byte. And when the VSync finishes, it goes high, we start counting with our most significant byte, and that counts 0 to F, and then I've zoomed in on the bottom here, and so the least significant byte also goes 0 to F for every single one of the other higher most significant bytes. So therefore we get a count from 0, 0 up to FF. So that's what that counter is doing. Now it's important to mention that the 0 to FF is effectively each counter. So each one of these is this H star is basically, or H is the H blank. So each one of these is a line on the screen. And then we know that one of these, a VSync, is a whole screen worth of data. So that's one screen, another screen, another screen. So what this is effectively doing is each line we get a new count. So this V count is effectively the number of lines going down the screen. And so there's 256 because there's 0 to FF, which is 256. Now, as I said earlier, they're not all visible. Some are cropped, top and bottom. But that's what that count is doing. It's counting basically the number of horizontal lines on the screen. So in our example, we remember we had 4882 as our input. So these chips take in the counter that we've seen. We have one chip for the most significant byte, 2H, and one for the least significant byte, 3H. And for each, we add the bullet position, and the output sigma for each chip are then put into the 8-input NAND gate. The NAND gate will be 1 most of the time, unless the output from 2H is F, the output from 3H is either C, D, or E, and the H blank, or the 256H, is high. So really it's only passing a 0 out during the H blank period at the beginning of every horizontal line, and then if the sum of these is FC, FD, or FE. Now the flip-flop here is clever because it filters the result to only be relevant when the right coordinate is FC, FD, or FE. We'll see it filters it only when the vertical coordinate matters, and the remaining circuitry here just makes the pulse output to be a particular duration. So this output of 5E becomes the main important output for the vertical offset circuit. Looking at the traces, this first one shows all of the elements of the vertical delay circuit we've just gone through. We can see that this F3 out from the NAND gate goes low 4 times. 1, 2, 3, 4. These two are during the VSync, and they're just actually when the counter equals FC to FE, and they're not looking at bullet data. So this is always going to happen, but it's not relevant because it's during this VSync period. so is just excluded. The other two times we have F3 out as low are the two times when the sum of each vertical and horizontal coordinate is equal to FC to FE. Now if we take a closer look in this diagram, we have the bullet loading here during the H blank. So 256H is the H blank, and we're loading the bullet horizontal and vertical offset 8 times, as we said. So horizontal and vertical offset, and we do that 8 times. So you can see here we have 7A, and when that's added to 8,2, which is the coordinate for the horizontal offset, we do get FC. And when we get FC, this goes low for the F3 out. But note that the E31Q doesn't change, and that's because it's filtered by this H8. So the flip-flop, what the flip-flop does is the rising edge of the flip-flop is clocking on H8, and this is always positive when this clocks, and therefore this doesn't change. And so what that does is filters out the 8,2 portion, because it only wants it to be coming through when it's 4,8. So if we go over to this one, this is that other one, except instead of the 8,2 equaling FC, it's the 4,8. So this time B3 plus 4,8 equals FC. And again, when it equals FC to FE, we go low with this F3 out. This time we are clocking on the H8 on the negative, or the low. And so it does go through to the E5 out. And therefore we get our vertical bullet filter acceptable. I have to say it's pretty ingenious how they've done it. It's hard enough to work out these circuits, but to actually come up with it originally, I really am in total awe of that. Now this diagram here is showing that in this area after the H blank, the vertical delay circuit doesn't do anything. And so we're really only interested in this part here, but for the vertical delay circuit, but now we need to have a look at the horizontal delay circuit to see what's happening. So here is the first part of the horizontal delay circuit. It's got the same input latched from the 2L chip, and so the data goes both ways. And as before, we have a most significant byte and a least significant byte. The most significant byte goes into the 2E chip, and the least significant goes into the 2F. And these are 74LS163s. Now we've seen the 161 counter chip a bunch of times, and the 163 is very similar. If you look at the diagram, you can see the main difference between the 161 and the 163 comes when we have the clear. Now you can see here on the 161, this is an asynchronous clear, which basically means once we get clear, instantly we go from the counter straight down to 0. Asynchronous means not related to the clock. Now the 163 is synchronous, which means when we have the clear goes low, it waits until the next clock cycle to go low. And so that's the difference between the 161 and the 163. Now the reason why they're using the 163 in the design of these counters, I guess, is to do with getting the timing right. Looking at the timing that I've seen, I don't really understand why they need to do that. It looks like it all works fine anyway, but I'm sure there may be some instances when it's not doing that. So back to the timing circuit, we see that the horizontal counter has two phases. One during the H blank, when it loads data from the 2L chip when 4D output 3 goes low. Then the second is just after the H blank, when its count is based on the 6 MHz pixel clock. And so it's counting from 0 to FF horizontally every pixel, using the two counter chips. Prior to starting that count, it's cleared to 0 by the 4D output 2. Now note, this is where I think that the schematic is wrong, because it shows in the schematic output 1, but pretty sure that should be output 2. So if we go over to the diagrams, we've got, as I say, the H blank period that is constantly reading in the bullet data, and then we've got the period after the H blank when we're just doing a normal count from 0 to F. And if we go into this one here, it's just a zoomed in version. So as we see on every load, this is a load, we go 82, 48, 82, 48, it's just loading in these numbers. And then after that, we've got it counting normally. So it starts at 0, 0, and it'll just count 0, 1, 2, 3, 4, 5, and so on. The last block of the bullet circuit is the horizontal delay circuit. Effectively what it does is uses a RAM chip to store the horizontal location of the bullet, and then it allows it to be plotted once it gets to that horizontal point along the screen. The main component of this block is the MB8125 RAM chip, or otherwise known as a 2125 RAM chip. This is a 1024 location by 1 bit wide RAM chip, and we don't use all the space for this RAM chip. We're only using 8 of the address inputs. In our circuit for the inputs, we have the chip select is a combination of 256H star, which is an offset of 256H, or the H blank, and that's ANDed with the 5E. Remember, that was the output from the vertical delay circuit. And then we have data going in, which is the 256H, so it's only going to be high during H blank. And then the write enable is enabled on the 6 MHz pixel clock. And then the address input for the RAM chip is that counter that we had, either the counter or during the H blank, the storing period. The output to the chip comes out here, and it's filtered by this D flip-flop, which is clocked on this not 6 MHz prime and has a clear of the not H blank star. So the output Q of this, of the 3E flip-flop, is actually the final bullet renderer output that goes into the PROM that we saw earlier. So if we look at this first plot, this is the entire V blank to V blank. So it's a full screen worth of data, and we just see this blip here from E5 out, and also from the D2D and E3Q. So that's the bullet going all the way through on the screen. But really this view is zoomed out to show what's really going on. So what this is doing is plotting, roughly halfway down. If you imagine this is the beginning of the screen vertically, and then that's the end of the screen. This would be FF in our imaginary sprite picture, and that's 0, that's 48 along the top there. With the zoomed in view, we can see how the counter works. So during the H blank period, the RAM is fed with values of the bullets. But you can see in this diagram, it's not enabled during this time because C53 is always high. And C53 was the chip enable. So it being high, it doesn't actually record any of this data. After that, the RAM is triggered to just count all the way through the RAM from 0 to FF. Now look what happens on the diagram below. So this time we have 48 plus the offset equals FC, as we've seen before. So now it essentially records the values in the location 82, 83 and 84. And since our bullet data is repeating, it does it a few times. Now it doesn't kick in straight away here. There's this period here, but that's made up on the end. So there's three sets of lines of bullet data. So this is the same but it's the next horizontal line down, we can clearly see that the bullet is being saved to the RAM for each of the bullets into 82, 83 and 84 locations. 82, 82, 83, 84, 82, 83, 84, 82, 83, 84. So that's the saving part, and then the next clever part is shown in the next plot. This plot is for the remaining part of the line after the H blank. You can see that when we get to 82 along from the edge, we start to go high, which means the bullet is starting to show. So there you have it. Just to go over it one more time. So the renderer takes in the bullet position data and checks for the correct vertical position. If it's not the correct vertical position, nothing is done. If it is the correct vertical position, then during the H blank, the correct horizontal position is stored into a 1-bit RAM chip. And then on the same line plot, after the H blank, the bullet is then plotted when the line counter reaches the correct horizontal position, and it essentially plots what's been stored in the RAM for that line. So when we fire up the core with just the one bullet on there at 4882, we do have actually, interestingly, garbage at the top of the screen there feeding into the video memory. Now that wasn't there during the simulation, so it shows, you know, differences between simulation and FPGA. For some reason the FPGA is getting that data through there. Now what we can do is spread the bullets out, all 8 of them, into different parts of the screen as we're showing here. Just to show roughly the extremes of the screen and a diagonal in the middle there. And so let's take a look at how we implement that in Verilog. So for the Verilog code, we're back on the GitHub on episode 14. And we've got 5 folders. We've got the Tank FPGA CRT, the VGA version, the Tank Sim that we've been using for the waveform traces we've seen so far in the episode, and then we've got this alt CRT files and alt VGA. All that is later on we're going to fire up the original core that we saw last week, but we're going to have the bullet included this time. And all that is just a change to the ROM file. Effectively in the Tank FPGA we change how the ROM is set up, but we'll get into that. So if we look in the CRT folder, first one to look at is TTL chips. Now all we've added is 3 chips on the end. So we've got the LS163 that we saw, which is the synchronous reset and clear, rather than the asynchronous one for the counter chip. So really here, this is the meat and potatoes of it, is the clear is inside the clock for the always block. The sensitivity of the clock there triggers the action, and then it checks if we're on a clear. So it's clearly that's gonna, you know, wait till we have a positive edge of a clock. If we compare that to the 161, the 161 is here, and you can see we've got either a positive edge of clock or negative edge of clear. So that instantly triggers that, so without necessarily anything to do with the clock. So you can see the difference there in that one. That's a 163. I have added a module for the LS10, which is a 3-input NAND gate. We didn't actually use that in the final model. You don't need to. It's really just a very simple line. If things get super simple, there's really no point in implementing a chip. I was just doing this for completeness. Same with the LS08, which is a quad 2-input AND gate. And then we've got the LS283, which we do need, which is the summing chip that we've seen. Pretty simple. It takes in an input A, an input B, and it sums it. And we've also got this carry. Now don't forget, with this chip it can be either the high or the lowest significant byte, so it has an input to the carry as well. And so quite a simple module there. So that's TTL chips. In terms of the RAM, now for this particular one, we've got two new RAM modules. Bullet RAM was this one, and I just created this module so I could load the bullet into the memory. As we've seen, I loaded that 4882 bullet into the lowest part of the memory. So the way to do that is just to load this file, and then we have a specific section for this bullet RAM, but we don't need that usually. And then we have this module RAM 8125, which is that 1024 by 1 bit RAM. This is actually no different at all to the other RAMs we've had. It's just smaller size. I think we had 2K RAMs, this is 1K. And so we've got a 7 down to 0 address, 8 bits wide. The actual chip for the 8125 is bigger than that. It's got more address lines, but we only use 8. It's got one input D in, and it's got an output Q, 1 bit as well. So then the last thing that we changed is up in the tank FPGA.v, and I've only added items down at the bottom. You can see here, just for the RAM, as I was talking about, I grayed this one out, which was the normal RAM, and then I put in this bullet RAM, which was specific to loading that bullet file, which was just the 8 bullets in that lowest area of the memory. All the rest is the same. And then we've created the 283 chip. So obviously, as we've seen, the input A is the counter, so the V's, same here, and then the input B is from the 2L chip, so here L2Q is the output, so it's 3 down to 0 and 7 down to 4. Our input carry is 0 for the lowest significant byte, and it's that chip for the highest significant byte. And then the sigma, so the output, I've just created some wires called sigma, and they get fed in later. And then for that one, that has no carry output. And then for the flip-flop, we've seen that flip-flop before, so it's just a matter of wiring those up. Now, one thing to mention is this NM6 prime is not clear on the schematics what it is. So I took a guess at what that is. And I think that's just an offset of the earlier 6 megahertz clock. And that seems to all work just fine. But I really had to guess that one because that doesn't go anywhere. It doesn't exist on the schematics. So all of that basically outputs to this E31NQ. And then down here, we have this E5 out, which is the final output of the vertical section of the bullet renderer, as we've seen. For the horizontal section, as we've seen, we had a 163, the two 163 chips. Again, it's just a matter of connecting these up properly. So nothing totally new here. The inputs are from the L2 chip, as we know. The clock is the 6 megahertz clock. We load from that D42Y output 3, as we saw in the schematic. And then the clear was the D42Y pin 2. And as I said, it was 1 in the schematic. And then down here we have our RAM instantiated, with the D in being the H star, 256 star, the address being the output from the counters, write enable the 6 megahertz. It needs to be write enable low. Then we've got a clock. There is no clock in the actual memory, but for memories in FPGA we put a very high clock on there. Chip selectors are C5-3, again it's low, so we make it chip select low. And then our output is D2D. Now let's not forget the PROM chip, which is where it all goes out. We have to add our E3Q here. Before that was 0, if you remember. We set that to 0 because we didn't have a bullet circuit. Now we do. We're going to put the proper input in there, so E3Q must go into the PROM, otherwise we won't get anything. And that's it. So it's pretty simple to implement this in Verilog. And now we've got everything functioning in terms of our rendering system. We've got our tile rendering system and we've got our bullet rendering system, and that's all we need. Now what we can do is we can remove the constraint of the bullet memory and let the CPU fill it in as normal, and when we fire up the core we get this test pattern running again, but this time in the background behind the tiles we can actually see, if we slow it down, we do have the bullets doing a test pattern as well, and so that's totally normal, and that's what happens there. So in summary on this one, what we've done is we've implemented the bullet circuit, we've explained how it works. I think it's a really clever little design, and as I go through understanding arcade hardware, maybe I'll see more that sprite hardware works like this with more colors. I'm not sure, I'm yet to find that out, so it's a good journey to be on. Next time what we're going to do is implement the interrupts properly to allow the game to carry on into the attract mode, and we can also implement the MiSTer framework around it as well. So we'll be back doing that in the next one, so see you then.